Now, one important thing about canonical ensemble, of course, the most important thing is the systems in this ensemble exchange energy with the heat bath till the temperatures are equal. So in that sense, we expect some fluctuations in energy. It may fluctuate about the average, isn't it? There must be an average energy. And since the energy exchange is going on till equilibrium, even in equilibrium, there may be some fluctuations, small fluctuations. So let's calculate that fluctuation, okay? If we are going to deal with grand canonical ensemble, in addition, we have fluctuations in particle number, isn't it? Because particles are being exchanged with a particle reservoir. Here, we only have energy fluctuations. The number of particles are fixed. They don't fluctuate. Let's calculate this energy fluctuations. An extremely important problem again. In canonical ensemble. Let's start from the mean energy. Mean and average are the same thing. So average energy is the internal energy, if you like. That is, well, multiply with the probability and sum. That is the expression, isn't it? Is that okay? This is nothing but multiplying the energy values with the probability and some overall possible states. Now, to get to the fluctuation, I will take derivative of this with respect to beta. Take very simple derivative of that expression with respect to beta. This gives us, very simply, if you take this as the first term, multiplying 1 over that term, derivative of first times second, this first times the derivative of the second, isn't it? Very simple derivative. Let me do it at least this much. Derivative of the first one with respect to beta. Beta brings down an ER minus ER. So the sum becomes sum over ER squared e to the minus beta ER, multiply with the second, which is 1 over this term. Okay. And now let's take the derivative of 1 over the sum exponential. That derivative becomes minus, again, 1 over, well, how do you take 1 over something derivative? Derivative of first is 0 times second minus derivative of second times first divided by the square. Huh? So 1 over the sum square times minus ER derivative e to the minus beta ER. Of course, you have to multiply it with the first one, which is, first one is ER times e to the minus beta ER. Is that okay? Very simple derivative. Well, what is this? That is average of energy squared. Multiply with probability, so it's minus E squared average, isn't it? And the second term is the square of the E average. So it is plus average E squared. We find the fluctuation this way. So it becomes delta E squared is E squared minus E average squared, and that must be negative of my result. Now I can take this derivative of u with respect to beta as derivative with respect to temperature, isn't it? Because this is nothing but minus del T del beta du dt. Well, keep the ER constant. And this is nothing but, what is that du dt? Heat capacity, isn't it? CV, in other words. If it is enthalpy, it is Cp, as you remember. And we know that because beta is 1 over kBt. If you take derivative of kBt, 1 over kBt with respect to temperature, you get minus 1 over kBt squared. So the result is, since this is inverse of it, kb t squared times Cv. That is the fluctuation. This is extremely important. Whenever we calculate the fluctuation, what is delta E in quantum mechanics? Uncertainty, isn't it? You have to remember this. You have to relate the courses to each other. You have to transfer your knowledge in one to another course. So this fluctuation is proportional to kBt squared times a response function. This is a response of the system to a given heat. If you give heat to the system, it is a measure of how its temperature changes, isn't it? It responds to the heat you introduce to your system. So you shouldn't look at these as simple derivatives, but all of them almost have physical meaning. You should try to understand that physics. So, as you are going to see later, this is an example of dissipation, this fluctuation problem. Okay? Extremely important. You are going to see it later. Now, let's look at the relative root means square. Root means square. When you take the square root, that means square root delta E squared E is KB T squared CB divided by U. This thing must be of the order of one over the square root n, where n is the number of particles in the system. When n is large, that thing is very small. Fluctuation is negligible. RMS fluctuations are negligible. If a fluctuation is negligible, then the energy is equal to the mean energy, isn't it? So you can take the energy of your system as the average energy. So it is another important thing about finding the average values, where statistical mechanics is giving you these averages. Okay? Now, there are also two theorems, equipartition and virial theorems in this chapter. I want you to go over them. Probably you have done that in your undergraduate course. Extremely important. I will keep on going with the examples, dealing with the canonical ensemble, and I will do the paramagnetism problem now. Is that okay? Have you done this problem in undergraduate course? No? Okay, very straightforward application of canonical ensemble ideas. So I think you are going to see a physical example, not a toy example, of canonical ensemble. Do you have any questions with this? Read and write. Do your homework. Now, paramagnetism. What do you know about magnetism as a whole? Do you know something about magnetism from your general physics course? What types of magnetism have you studied up to now? See, even the general physics course is quite useful in statistical mechanics. What type of magnetism do you know? Ferromagnetism, the strong magnetism, isn't it? The magnets you use at home to pick things up. That's strong magnetism. We cannot do that now because we are still doing the ideal systems, non-interacting systems. Ferromagnetism is a result of spin-spin interactions, locking the spins in the same direction. So you have magnetism even in the absence of an applied magnetic field. Now, there's diamagnetism, where when you apply a magnetic field, an opposite magnetic dipole moment is generated, so it is a negative susceptibility. Okay, you get a magnetism not in the direction of the applied magnetic field. It is orbital motion of the particles, electrons mainly. I will probably do it for you as an extra thing. But paramagnetism that we are going to do now is a magnetism coming from spins orienting themselves in the same direction when you apply a magnetic field. Why do spins orient themselves along the magnetic field when you apply a magnetic field? Because there's a torque on the spin. It's mu cross V, isn't it? The torque that turns the spin in the same direction as the applied magnetic field. This is general physics that you have to know. Okay, let's do paramagnetism. Here I'm going to consider a system of n magnetic dipoles. So the system to be magnetized is n magnetic dipoles with magnetic moment of these dipoles denoted by mu, as usual. So apply a magnetic field and you have magnetism created. So it creates magnetism. In the sense that it aligns these magnetic dipoles by applying a torque on each one of these. Do you know any other influence that may kill magnetism? What does kill magnetism? Well, for this you have to have fluctuations, isn't it, that will take the spin against the magnetic field. Fluctuations are results of temperature, isn't it? When you increase the temperature, they will jiggle more, and they may go in the opposite direction. So that kills the magnetism. So thermal agitation, if you like, jiggling, in other words, kills magnetism, or temperature kills magnetism. So in this problem, then we expect a competition between applied magnetic field and temperature. So we have to see the applied field effect along with temperature effect, kBT. Let's see. If temperature goes to 0, we must have complete magnetization, isn't it? If temperature is very high, the magnetization must die. We must get rid of it. Complete randomization. So T going to 0K, complete magnetization and t going to infinity, complete randomization. Because at very high temperatures, spins become completely random. If they are random, there is no magnetization. They cancel each other out. Up, down, okay, they cancel. So the important parameter then at intermediate temperatures is this. Temperature and mu h. Mu h is, of course, the potential energy, isn't it, of a magnetic dipole moment in a magnetic field. It's minus mu dot h. So mu h is the magnitude of that magnetic energy. Then this is the thermal energy. So you have to compare these two energies. If this is small, then temperature is big. That's the classical limit. If this is big, then magnetic field dominates and temperature is small. Okay? So that's the important thing. Now let's model. Statistical mechanics is model dependent. We have to model the system to be able to write something thermodynamical about it. So let's model this system. We can do it in two ways. One is the classical dipoles, the other one is the quantum dipoles. Let's take it to be classical first. Let's see what classical physics is going to tell us. So, let's model this. N identical, okay? There is no distinction between magnetic dipoles. Localized, meaning that they have specific positions. So these are distinguishable, isn't it? So we know how to go from one particle partition function to n particle partition function if they are distinguishable. We don't have to divide by n factorial in this case. Okay? Non-interacting, because we are still doing ideal particle physics. No interactions between particles. Non-interacting. And freely oriented, isn't it? This is the classical part. Freely oriented means this goes any way you like. In quantum mechanics, it is not possible. Dipole moments can only be oriented in certain directions. Angular momentum, quantization of angular momentum, remember. But in classical physics, there is no restriction like this. So, that's our model, freely oriented dipoles. That's our model. Each one of these have physical consequences. We have to know what they mean. So let's write the energy for the system. sum of individual energies of these. Let's take n of them. Total energy of the system is the sum over n dipoles, each one having an energy EI, and of course that energy is minus mu dot h, so it is minus mu I dot h. So the ground state in quantum mechanics is where the magnetic dipole moment is in the same direction as the magnetic field, so dot product gives you a positive quantity and energy becomes negative, lower. Excited state will be plus mu h because they are going to be in opposite directions, down state and up state. Okay. Now we can write this as minus mu h, and sum can be restricted over the cosine of the angle between them, isn't it? That product brings down a cosine of the angle between two vectors. And the partition function can be written as one particle partition function to the power n. No division by n factorial because they are distinguishable particles and localized. So you can write this, well, one particle partition function as, well, we know the energy, e to the minus beta e, isn't it? So sum, what are we going to sum over? The theta, that's going to change e to the beta mu h times cos theta. Theta is the angle between mu and h, dipole moment and the magnetic field. Well, if we calculate the average of the magnetization, we will find it in the direction of the magnetic field, isn't it? Magnetic field will turn the spins in the same direction with itself. Of course, it also depends on the temperature. If temperature is high, we are going to get half of them in the same direction, half in the opposite direction, because there will be switching over because of thermal agitation. So, magnetization or mean magnetic moment, mean average magnetic moment in direction of the magnetic field has a magnitude. Let's apply the field in the z direction. Okay, so we are interested in the z component of this vector. Should be an average of this quantity that will be, we can write the average in terms of angle, mu cos theta, e to the beta mu h cos theta divided by e to the beta mu h cos theta. Okay, that's the average. Multiply the quantity with the probability and sum overall possibilities. That's the average, the way we take averages. Now let's continue. You can rewrite that, if you like, as n over beta derivative of ln q1 beta. Okay? Here is q1. Take logarithm of this. Derivative of the logarithm is 1 over the function times the derivative of the function. Exactly, that expression results. Okay? So, this is also derivative of Helmholtz free energy with respect to applied field at constant temperature. You have to know something about thermodynamics of the magnet. Usually you have gases, PVT systems, pressure, volume, temperature systems, but if you have a magnetic system, a material, you have to know how thermodynamics changes. Let me remind you what happens to thermodynamic laws. If you have a magnet, recall, of course, it comes at this point. Recall that the first law and second law combined turns out to be MdH. There is no particle exchange, no chemical potential term like this. But here there's an interaction with the external field. So thermodynamic first and second laws can be written combined law in this form. M is the magnetization we are after. And the Helmholtz free energy, U minus Ts, has the following form in terms of this. It is du minus Tds minus sdt. Put that du in, you get rid of Tds terms, so it becomes minus s dt minus m dh. This is the reason why we have dA dh minus to get m, isn't it? At constant t, this term is 0. You have m as minus dA dh. Exactly what I have written here. Okay? That's where it is coming from. That's you should remember that from your undergraduate statistical thermodynamics. So, the quantities of interest can also be written as follows. Heat capacity at constant magnetic field is just like before. It is du dt at constant magnetic field. Magnetization is minus del A del H at constant temperature, as I have shown you. And susceptibility at constant temperature is isothermal susceptibility, del M del H at constant T, isothermal susceptibility Now, some look at this as a derivative. Yeah, it is, but what is the physical meaning of it? Do you remember something when somebody tells you about susceptibility, magnetic susceptibility? What is it? What is the physical meaning? Just look at this expression and tell me. You know, I like physical interpretations of everything. What is this? Well, to me it says, what happens when you change the magnetic field, apply the magnetic field, change it, delta H, by some amount, how much the magnetization changes. So, how easy or difficult to magnetize a system, isn't it? It's the measure of that quantity. So if this is small, what does that mean? I apply a high magnetic field, I get small magnetization. It is difficult to magnetize that system. If it is large, it's very easy to magnetize that system, isn't it? I apply a small field, I get a large magnetization. So in thermodynamics and statistical mechanics, I think just like in other fields of physics, you have to look at these definitions carefully to really understand its physical meaning. You can remember that, but susceptibility may, if it doesn't make any sense for you, you don't remember it, isn't it? You just forget it.
Is temperature constant?
That's why I said isothermal. Isothermal means temperature is constant. You have to measure this in lab, keeping the temperature constant. Just apply the field and see how much the magnetization changes. Okay? At constant temperature, of course. Isothermal is. So, the system is paramagnetic if this susceptibility is positive. Chi is positive. That means magnetization is in the same direction as the magnetic field. And the magnetization is parallel to the magnetic field. That's paramagnetism. Well, of course, this chi cannot be very big in paramagnetism. Positive, but somewhat smallish. Diamagnetic, the system is diamagnetic. This is a summary of general physics for you. If chi is negative, chi negative means magnetization is opposite to the applied field. Huh? And ferromagnetism ferromagnetic, strong magnetism, as a result of strong dipole-dipole interaction, M is going to be different even when the magnetic field is 0. Well, of course, you have to have hysteresis here. Apply a magnetic field, align the domains in which the spins are already aligned with respect to each other in the same direction as a result of strong dipole-dipole interactions. So when you apply the magnetic field, all the domains are going to be in the same direction. That's strong magnetization. And if you now reverse the magnetic field and make it to be 0, you still get magnetization. Dipole-dipole interaction. So it is particle-particle interaction, if you like. It's not an ideal system. We are going to study this ferromagnetism using the Ising model or Ising model as an example of strong interactions between particles when I do the interacting systems. Okay? So now we are going to concentrate on that. Chi is positive, not very large, but positive. We have paramagnetism, aligning spins in the same direction. Okay, so that is a summary of magnetism for you. So to study this, all we need is the one particle partition function, because we can get magnetization as a result of that. We need single particle partition function, Q1. So need Q1 as a function of temperature, which is when we are doing the classical theory, isn't it? We call that Langevin theory. Do you remember these terms, these names? Very important names associated with this problem. Is it coming back to your mind? No, you have not seen it. Oh, very nice. Completely new problem then. Huh? Well, let me write the Langevin theory, 1905, important year, remember, for physics. Let's do that integral. It's the beta mu h cos theta sin theta d phi Langevin Langevin 1905. Miracles here. Why it is an important year? Einstein. Okay. This turns out to be 4 pi sinus hyperbolic beta mu h divided by beta mu h. You can do the integral by calling cos theta x, then sine theta d theta is dx, isn't it? Do the exponential integral and you have sinus hyperbolic, 2 exponentials. Is that okay? Can you do that? Good. So this gives you an average magnetic dipole moment along the z direction total magnetization per particle, average dipole moment, in other words. This turns out to be, well, you should do that too because it involves a derivative. It is 1 over n over beta, del H, ln Q1 beta. Do this. Always do the calculations. I don't want to bore you on the board doing the calculation myself. I will do the important ones, of course. You have mu cotangent hyperbolic beta mu h minus 1 over beta mu h, and we call this a function L beta mu h. L, you might guess, is the Langevin function. Langevin function, L of x. Well, it is cotangent hyperbolic x minus 1 over x. Very simple. X in our case is beta mu h, isn't it? In our case, x is beta mu h, or mu h divided by kbt. I told you this is an important thing that defines the physics. If you plot this function, you get something like this. Here is the function. X, L of x. Well, there is a region where we have kind of linear behavior, then there is a deviation which goes to a limit 1, 0, 0.5. This part is like 4, like 8. So, if we have, I will ask you why it has to make, well, it has to go to a limiting value. Think about it. If we have n0 dipoles per unit volume, that means total number of dipoles, n divided by volume, v. This is the number of dipoles per unit volume. Magnetization of the system then can be written as n0 times mu z average, mean magnetic dipole moment, and it is n0 mu L of x. We are a little bit over time, but we are about to finish. Let's stop here. Okay, let's give a break. Come back for the last lecture for today. We are almost there, isn't it? So, Langevin function gives us all the information. Why do we have this limiting form? Anybody? Any suggestion? Well, you have a certain number of the magnetic dipole moments. The limit is you can put them in the same direction, almost all of them. Since this is a well-known number, we don't have any more to align, isn't it? You can align only n of them. There must be a limit